Today we're going to look at the end behavior and turning behavior of a polynomial function. Now perhaps you're even just first saying, well, what is end behavior and turning behavior? Well, end behavior ends up being what the graph is doing to the far left or to the far right. It's what happens at the ends of the graph. Again, on the far left or far right. Turning behavior, well, that's just literally the graph changing its direction as it travels from left to right. Now, both these things you probably have noticed happen, or maybe, both these things you probably have noticed are happening with functions, but today we're going to figure out a little bit more of why and how can we connect them to an equation. So let's start by remembering, honestly, the different degrees of a polynomial. We're going to start by classifying a polynomial by its degree. Now I say remember this because, well, the truth is you've done this already. But let's recall. This graph right here is a straight line. Straight lines are called linear, which means that their degree, which is the highest exponent, is going to be to the first power. So we say x to the first, or maybe just x. The second graph that we have, it's a parabola, so it's going to be quadratic. Quadratic, remember, means that the degree, or the highest exponent, is 2. So it had to be an x squared. Now this third graph is going to be of degree 3. And a degree 3 is called a cubic. And finally, next we have a graph that's going to be to the fourth power. We may not have used this word yet, but we will today. It's called quartic. Quartic means to the fourth power. And our last degree is to the fifth power. And a fifth power is going to be quintic. Now, as you can see, each of these graphs starts to have different behaviors. So let's continue to analyze and now start to think about what's called the end behavior of the graph. The end behavior, what is happening as we look at the far left or the far right. Now, I'm only going to do this for some of the graphs in case you wonder why. I'm just kind of randomly choosing some of them. We honestly could answer the end behavior for all of them. So how about this graph here, this quadratic graph as x goes to negative infinity? Now, first you might say, what do you mean x goes to negative infinity? Well, that just means what's happening to the far left as x goes to negative infinity. So we look at the left of this graph, that is, we look at the end of the graph at the left, and we see that the graph is going up. Now, since it's going up, we know that it's going up to infinity. I don't write the word up, but rather I use infinity or positive infinity to describe, again, the graph going up. How about the cubic graph? The cubic graph is x goes to infinity. What does infinity mean as x goes to infinity? Well, that's going to be to the right. So we look at what's happening at the end of the graph on the right side. And we see once again that the graph is going up. That is, the y value is going up to infinity, or positive infinity to emphasize that. How about our last graph, our quintic? If I want to know what's happening as x goes to negative infinity, remember that's the left, what's happening at the far left. And now we see the graph is going down. It's going down to negative infinity. But as x goes to infinity, that means to the right, we see that the graph is going up. And so it's going up to positive infinity. So the end behavior is actually what's happening as I look at the far left and far right of the graph. It's either going up to infinity or it's going down to negative infinity. Do you think you can analyze example A for its end behavior? As x goes to infinity, that means I'm going to the right because it's x going to infinity. So I look at the right side of the graph, and I see that the graph is going down. It's going down to negative infinity. But as I look at x approaching negative infinity, because it's x going to negative infinity, that means we're looking at the left of the graph. So we go to the end, the left end, and we see that the graph is going up. It's going up to positive infinity. X to positive infinity, that means to the right. That means, we look to the right, and we see that the graph is going up. X to negative infinity means we look at the left. What's happening is the graph, on the left side of the graph, it's going up. And so end behavior is what the graph is doing to the far left or far right. Perhaps you're wondering, well, why do some of them seem to go up on both sides? Maybe down on both sides, or maybe up and down on opposite sides. We have another connection to make. We're going to make a connection now with the degree and the end behavior. The degree and the end behavior. Let's go up here to our, I got to get rid of some of the extra marks here. Let's go up here to our cubic graph. Our cubic graph. And I want you to notice that, first of all, a cubic, that is x to the third power, is an odd power. Next, I want you to notice that its end behavior seems to be opposite. That is, one side is going up and one side is going down. How about our other odd graph, this quintic? Again, it's an odd degree. And do you see how each side, or the end behavior sides, are opposite? One side goes up and one side goes down. It appears that when we have an odd graph, that indeed the end behaviors are opposite. So what about an even degree? What about an even graph? If we go up here to one of our evens, maybe this x squared, we see that the end behavior, that is the left and the right side, are both going the same direction. How about our other even degree? Same thing, they're both going in the same direction. It turns out that when the degree is even, then it is true that the end behaviors will be the same. Now, there's a really neat way to memorize this. Have you already noticed? Odd for opposite. Doesn't really work over here as nicely, but even for same. Odd for opposite. So how do you know if this side or that side is going to be the side that goes up or down? Well, there's one more connection. There's really one more thing that we need to look at. And that is that we're going to have to look at the leading coefficient. Now, the leading coefficient, you're going to discover, is very important in understanding what happens as we go to the right. I feel like we should have you fill in the words leading coefficient somewhere here too. So let's see if we can sort of fix this up a little bit. The leading coefficient, that is the number that's in front of your highest exponent, is going to have everything to do with what's happening to the right. Now, to understand this, what we're going to do is we're going to type these equations into a graphing tool. How about something like Desmos? Now, you could fire up Desmos if you want on your phone or computer, or you could just watch me, which is fine. I'm going to record y equals negative 1/2 x to the fourth where do I get my fourth power here? I don't have the full keyboard. I should have been better prepared with this. I guess I'll just overwrite the exponent of 2. That'll work just the same. So I've got 1/4, yeah, negative 1/2 x to the 1/4 plus 2x squared. I already got the square there, and then plus 3. All right, so we get a pretty cool looking polynomial graph. Sort of looks like maybe the golden arches. What we want to do is we want to draw that, or maybe I should say just kind of sketch that graph here. But what we also want to do is we want to notice what's happening to the right. We want to notice what's happening to the right. And indeed, it looks like to the right, the graph is going down. Now, the graph is going down to the right, and my leading coefficient is negative. That's going to be something worth repeating. So it looks like, as I look to the right, I see the graph going down, and we have a negative leading coefficient. Let's look at this next one. We've got, what do we got here? We've got negative 2/3. I'm just going to write over top of some of this stuff. So negative 2/3 x to the 5th plus 3x minus 4. We get another cool looking polynomial graph. We'll draw a quick sketch of that. That was interesting. Let's try this again. We'll draw a quick sketch of this. And again, we're going to look at the graph's behavior to the right. Once again, we see that to the right, the graph looks like it's going down, and our leading coefficient indeed is negative. Well, what happens if our leading coefficient is positive, like in this third example? X squared minus 5. Now we can put x squared minus 5 into Desmos, but you may already have an idea of what that's going to look like. Remember, x squared is going to be a parabola, and if we have a minus 5, it's just going to be shifted down 5. But what we want to do is draw a sketch of that parabola and look at what's happening to the right. Well, look, it looks like it's actually going up to the right, and the leading coefficient is positive. I think we have a conclusion here. If you think about the leading coefficient, it's going to tell you what the graph does to the right. And then if you look at the degree, it's going to tell you what is happening with both the left and right. And finally, you put all that together and you'll be able to describe the end behavior. Now, did we go too fast over that? Let's just kind of go through it again. If you look to the right, or I should say if you look at the leading coefficient, if it's positive, you know that the graph is going to go up to the right. If it's negative, the leading coefficient, that is, if the leading coefficient is negative, the graph's going to go down to the right. So it's all about the right. But then if I look at the degree, an odd degree means that, well, that the behaviors then on both sides will be opposites. But if the degree is even, the behavior on both sides will be the same. And if you put that all together, you'll be able to describe the end behavior of the graph. Let's see if we can do it. We're going to flip over to the next page here. What we want to be able to do here is we want to be able to completely analyze what's going on with, the end behavior of this graph. So my leading coefficient is the number in front of your highest exponent. It is positive. Now, since the leading coefficient is positive, you know the graph is going to go up to the right. The degree is the highest exponent. Here I have a degree of 3. Now, since the degree is 3, That's actually an odd degree. And if I have an odd degree, we know that we are going to end up with opposite end behavior. So, in conclusion, and I always like to make this kind of like a little conclusion box, because this is what we're trying to do. In conclusion, since the graph is going up to the right, that means that when I go to the right, that is when x goes to infinity, that the function or the y value is also going to go up to infinity. But when I look at the opposite side would be when x goes to the left, that is to negative infinity. And since the degree is odd and my behavior is going to be opposite, I know that my function is going to do the opposite of going up, which is going down to negative infinity. And I've just completely analyzed that for its end behavior. Want to try another one? I'm pausing because you may want to try this on your own. If you do want to pause the video. If you'd rather listen one more time, I'm going to begin now. Leading coefficient. It's negative. Since the leading coefficient is negative, I know it's going to happen to the right. It's going to go down to the right. Remember, the leading coefficient is always about what happens to the right. The degree. The degree is the number 4, but that's an even degree. Since the degree is even, I know that the behavior on both sides will be the same. It'll be the same end behavior. We're ready to make our final conclusions. What's the conclusions? It's what the graph is doing to the right, and it's what the graph is doing to the left. Yeah, you're always going to have both sides here. Sometimes kids will write both these down. But to the right, I already concluded that the graph goes down. That means f of x goes down to negative infinity. To the left, to the other side, well, to the other side, we know it's going to be the same. It's going to be the same end behavior, so that means it also goes down to negative infinity. Now it might make sense to fill in this little end behavior conclusion box. So our conclusion box, we're going to end up being able to say that if the degree is even, then we're going to end up with the same end behavior. If the degree is odd, remember, odd for opposite end behavior. And then the leading coefficient being positive means that as I go to the right, which just so we understand here, that's what x to infinity means. So as I go to the right, the graph will also go up to positive infinity. But if the leading coefficient is negative, that means that as I go to the right, remember this is always about the right, then the graph is going to go down to negative infinity. Now, that's a lot of things to put together, but that is your end behavior part of the lesson. There's one more thing that is part of today's lesson. It has to do with the maximum amount of turns, the maximum amount of times that the graph can turn, and the x-intercepts that you can predict. A linear function, degree 1. It does not turn. It's perfectly straight. But there is one x-intercept. It's right there. Degree 2. It turned once. It turned right here. That's one turn. It was going down. It was going down, and then it turned and started going back up. Be careful that you don't say that the graph just goes up. That is, it turns from going down to up. If you're saying that the graph just goes up, you're talking about the end behavior. But anyway, there's one turn right there. Now, this graph could, if it had been down here, it could have two x-intercepts. We're going to call this more 2 because of what it could have. How about this third one? The turns are going to be these two red spots. hold on, I'm getting ahead of myself here. This one's a degree 3. Make sure that you note that first. It's degree 3. All right, so we've got 2 turns. How about the x-intercepts? Well, now it looks like I have 3 x-intercepts. And how about this last one? When it comes to turns, 1, 2, 3 places that it's turning. When it comes to x-intercepts, 1, 2, 3, 4 x-intercepts. It seems like that the degree has a connection to the turns and the x-intercepts. If you even just look at this last one, it was a degree 4, and I ended up with 1 less turn, but I ended up with the same amount of x-intercepts. How about the next one, or the one previous to that? It was degree 3, I ended up with 1 less turn, but I ended up with the same amount of x-intercepts. Well, is that what's going to hold true with this degree 5 problem? 1, 2, 3, 4 turns. 1, 2, 3, 4, 5 x-intercepts. It seems like that the number of turns is always going to be 1 less than the degree. And how do you write 1 less than the letter n? N minus 1. But it seems like the maximum amount of x-intercepts is going to be equal to the degree. And that is what is true about your turns and your x-intercepts. Well, guess what we can do now? We can make a sketch. We can make a sketch of a function just by knowing a little bit about its degree and its leading coefficient. Or maybe we would say knowing a lot about them. But it's interesting, just the leading coefficient tells me that no matter what, this graph is going to go up to the right. Are you comfortable making the graph showing some kind of motion up to the right? And then the degree tells me that since it's odd, that we're going to have the opposite behavior to the left. Are you comfortable drawing something going down to the left? Now, the other thing about the degree is that it also gives me the max amount of x-intercepts. In other words, I can be sure that we're going to end up with, let's change the color here, I can end up with 5 x-intercepts. Now, do I know exactly where they are? I don't. But I know that I could end up with 5. And now if I try to connect the graph, if I try to connect like the full graph, then it would have to be such that it zigzags its way through these x-intercepts and then attaches itself on the far left and far right. And hey, by the way, how many turns does this thing have? Count them with me. 1, 2, 3, 4. That's 1 less than the degree, which again was 5. How about this second one here? Can you make a sketch just by knowing a little bit about the degree and the leading coefficient? Leading coefficient's negative. What does that mean? That's what it does to the right, right? It means it's going to go down. Degree is even. I was about to say odd. It's even. So that means it's going to do the same thing on the other side. Yepper, it's going to do the same thing. X-intercepts still connects to the degree. Remember, it's going to be the same. So I'm going to end up with 4 x-intercepts. And then what's this graph going to do? Well, you know it's going to have to zigzag as it connects and attaches to both ends of this graph. Now, the one thing we want to realize is that there's nothing for sure about the exact placement of these x-intercepts that I've given. The truth is that, just to show you, I very well could have 3 of my x-intercepts over on this side. Honestly, I could have all 4 over there too, perhaps. But let's say I had 3 of them over here. I want you guys to know that the graph can still do what it's supposed to do. That is, it's going to cross through those x-intercepts. And if we count the turns, I still get 1, 2, 3 turns, which is 1 less than the degree. So there's a little bit more that we need to learn, but for now we're just understanding that we can actually draw the graph based on just knowing a little bit of information with the leading coefficient and the degree. So what are you doing with that leading coefficient? You know that that's what the graph does to the right, right? What are you doing with this degree? It's odd, so you know that the graph is going to have opposite behavior on the left. Now, if it's going down on the right, if it's going down on the right, then my opposite behavior would have to be going up on the left. And then one more thing with the degree, it's the number of x-intercepts. Can I put 3 x-intercepts down? Sure can. And all we got to do is connect the graph as it sort of zigzags through these x-intercepts and goes down to the right, but up to the left. See how the turns kind of work themselves out? Yeah, I got 2 turns, which is 1 less than the degree.